Okay, so what I want to do today... Was that a careful way? Okay. So thank you for giving a demonstration of what the non-careful way is. Alright, so I'm going to go backwards, do accumulation points, and then we're going to go back and we're going to look at the integrals of sine of x over x and sine of x over x quantity squared. And for those of you who are taking the GREs, my condolences, but this will hopefully be useful. Alright, so the first is accumulation points. Okay, so F is holomorphic on an open omega. Sequence WK, k goes from 1 to infinity such that f of WK equals 0, and the limit as k goes to infinity of WK equals Z naught. This is not my notation, this is the book's notation. I think it's a little silly, hi friend Rami, that it's written like this. But they want to say, well, if the point is Z naught, and if you had a sequence ZK going to Z naught, you might be confused that Z naught is the first term of the sequence. And that's, is it working? Or it's not going to be fit perfectly. But if you used Z naught and you use the sequence ZK going to Z naught, you might be confused because Z naught is the first term or the 0th term of the sequence. That's why they're using WK for the sequence of points where the function is 0, and they're saying converges to some point WK. Then, if Z naught is in omega, have F is identically 0 on omega. Okay? So let's think about what this is saying. I have a sequence of points. My function is 0 for this for every term of the sequence. The sequence converges to a point in my space. Then my function is identically 0. Is this true for functions of a real variable that are holomorphic? So what's the real counterexample? So I want a function. Don't worry about it being infinitely differentiable. Don't worry about it being differentiable. Can you give me a function that's 0 and the set of zeros accumulates to a point?
Sine of 1 over x.
Sine of 1 over x. Excellent. Now, sine of 1 over x is not differentiable, so I have to take off a small amount. Can you make it differentiable?
Sine of 1 over x squared. Is that what?
No, that's going to be even worse in terms of differentiability.
X sine of x.
I'm not sure if x sine of x works, but something along those lines would work. If you do x cubed, you're definitely safe. Because when you take the derivative of this, you're going to get a 1 over x squared coming out. So I don't think x sine of x works. I'd be a little bit worried even just trying x squared. But x cubed, that's going to work. So here's a function, it's differentiable, and the zeros accumulate, but the function is not identically 0. So, yet again, complex analysis does not let certain functions in the door. Okay? So this result should be quite surprising. There's no analog of this in real analysis. Okay. So proof. What do we have? Did you have a question? Okay. So the question is, what do we have at our disposal to prove this? What do we know? I'm sorry?
Liouville's theorem?
We know Liouville's theorem, but that only works if the function's bounded, and we don't know if the function's bounded. And in fact, Liouville only works if it's bounded on the entire complex plane. This could only be happening on a small disk. What else do we? What do we know about the function?
It's holomorphic.
Holomorphic. So when you see the word holomorphic, you should have two thoughts.
Taylor series.
One is Taylor series, and the other?
Cauchy-Riemann.
Cauchy-Riemann. Okay. And a consequence of Cauchy-Riemann is integrals over closed curves. So these are the two paths you can be thinking for this problem. Either integrating along a closed path, or using the fact that holomorphic means analytic. And you're actually absolutely correct here that the one that really matters is holomorphic means analytic. And so what we know is F has a convergent Taylor series. At what point do we care about?
Z naught.
Z naught. So you told me it has a Taylor series. I get to choose which point. Well, the action is happening at z0. Here's my sequence of points converging to z0. So I want to expand things at z0. So eventually, what does this mean? It means that if I take a small enough neighborhood, I've got my Taylor series expansion about z0. So let's write f of z is the sum, n goes from 0 to infinity, of an z minus z0 to the n. There are two possibilities. Either the Taylor series is identically 0, in which case the function is identically 0, or the Taylor series is not identically 0. If all an equals 0, we're happy. Right? I'm trying to show my functions identically 0. I've got every coefficient as 0. I'm in great shape. Otherwise, there's an an that's not 0. Choose smallest m such that am is not 0. Now we can write f of z is am z minus z0 to the m 1 plus, and now I'll have the sum, and it goes from m plus 1 to infinity, of an over am z minus z0 to the n minus m. Right? I'm just pulling out that first term. Well, if z is really close to z0, notice n minus m is at least 1. What can you tell me about this? What does this look like?
At most 1?
I'm sorry?
At most 1? At least.
Not at most 1. I mean, how big is this going to be as z goes to z0? What do I know about that series? N minus m has to be at least 1. I've pulled out the z minus z0 to the m. The next is the z minus z0 to the m plus 1. Am I writing it right now? Yes. So as z gets closer and closer and closer to z0, what does that quantity look like? It looks like 0. So this converges to 0. If that converges to 0, there exists an r such that if z minus z0 is less than r, then above is at most 1/2 in absolute value. Right? If it's converging to 0, eventually it's no more than 1/2 in absolute value. Well, if it's no more than 1/2 in absolute value, is there any way this expression could be 0? Could 1 plus something that's at most 1/2 in absolute value ever equal 0? No. Why is this a contradiction?
Reason you have to say that am, the first term, is 0.
Why?
Because we know that that sums to 0, right? We know that that whole thing is 0.
Where do we know it's 0?
Because omega k is 0 for all.
Yeah, because we know for all these points omega k that are converging on z0, we have infinitely many omega k close. You give me any radius, r, and I still have infinitely many omegas inside that radius. But they can't be 0 anymore unless they actually equal z0. Yes?
So how did you get that it's bounded above by almost 1/2?
Well, I'm just saying eventually if z is really close to z0,
Yeah.
I have a series expansion that converges.
Okay.
And remember, there's a z minus z0 here to the first power.
Sure. Well, why 1/2?
Oh, I can take any number
Oh, it
less than
doesn't
any
matter.
number less than 1.
Okay.
Because now 1 plus, even if it was negative 1/2, that's not going to be enough to make this bracket expression 0.
Okay.
So I want to make sure this bracket expression is never 0. That's going to be my contradiction.
Okay.
So the way I'm going to do that is I'm going to show that it can't be greater than 1/2 in absolute value. And if it can't be greater than 1/2 in absolute value, this expression can't be 0. But this contradicts the fact that it's 0 for the sequence of WKs that accumulate contradicts f of wk equals 0 for an infinite sequence of wk that converges to z0. So what can we conclude?
It has to be 0.
AM has to be 0. So there's only the happy case. The only case that happens is every coefficient is 0. Alright, I'm thinking of a polynomial, I'm thinking of a holomorphic function, all of whose Taylor coefficients are 0, and because it's holomorphic, it equals its Taylor series expansion. What function am I thinking of? 0. Now this proves that my function is identically 0 in a small neighborhood of z0. So we've now shown is f is identically 0 in a small neighborhood of z0. So here's the situation. Here's omega. Here's z0. Here's a small disk about z0. And inside this disk, my function is identically 0. I now want to extend this and say the function has to be 0 everywhere. That in some sense, if you have a holomorphic function which is 0 in an open disk, then it's 0 everywhere. And so I'm not going to do the rest of this proof. The rest of this proof is in the book. It uses a little topology. It splits omega into two sets U and V. And it says basically if we take a connected set, there's no way this can happen. And so the only possibility is you look at U is going to be the set where my function is identically 0. And clearly that contains this open set here. You can show that that's an open set. You can also show it's closed because it contains its limit points. And you can show that you can't have such a decomposition. Now, this is going to cause us to go back here and look and see that maybe we need to change our definition a little bit. So I said f was holomorphic on an open set omega. It's actually not enough to claim omega is open. So in the book, they add one more condition. What condition do they add? So it's related to what we were discussing here. It's not enough to assume my set omega is open. I need one other thing.
Bounded?
Bounded? Nope. Good thing to try, but no. Need more than bounded. So I wanted to basically say that this whole thing fills up. What if this was, I'm sorry?
Connected?
Connected. And so, the reason I wanted to hold off on the assumption is to now see where it's coming from in the proof. What if I give you the following? This is my set omega, these two pieces over here. And I take my function to be identically 0 here, and I take my function to be identically 1 here. Is my function holomorphic? Yeah, it's differentiable here, it's differentiable here, these sets are separated. This is a holomorphic function, defined on an open set omega. Do I have a sequence of points that accumulate? Yes. And so this would be a counterexample. And the idea here is, I would get, not surprisingly, the function is identically 0 in a small neighborhood about a point. And then that would expand to this entire connected component. But it would not expand to all of omega. So we need to add omega is connected. And I hope you can see now from the proof why we need this assumption. Is that these two parts can exist independent of each other. And any conclusions we get over here cannot be transferred up to here. I can define my function however I want in these two places. They don't interact. So what kind of open sets do you think we should consider in this class? Henceforth, all of our sets should be connected, right? Because otherwise you just reduce the analysis to two different connected components. So it makes sense to study sets that are connected, because if they're not connected, we'll just analyze each piece individually. Okay? Any questions about this theorem? there's a really nice consequence of this theorem. It's a beautiful corollary. And so the corollary says the following. So, corollary. Fg holomorphic on open connected omega, sequence omega k contained in omega, omega k converges to z naught, and f of omega k equals g of omega k. What can we conclude? F equals g. Then f of z equals g of z for all z in omega. So the proof is one line. What function should I study?
-2.
Yeah. Study h of z is f of z minus g of z. And then just use the previous theorem. Right? So now because f and g are equal for that sequence, we now have a sequence where h is identically, where h is 0. And that sequence accumulates, so now we can use the previous result. Okay. So the question might be, who gives a, right?
So who gives a what?
This is being recorded. I have to stop there. It's a who gives a what. Okay? So why would we care about this? Can anybody give me a reason why we would care about this? Gives me a nice way to tell if two functions are the same. All I have to do is check on a sequence that accumulates. And if they agree on a sequence that accumulates, they agree everywhere. That's pretty convenient. So that's extremely powerful. If you've taken a probability class, you might have seen the proof of the central limit theorem. One of the questions in probability is, if I give you a sequence of moments, does that uniquely determine a distribution? And the answer is no, precisely because of this theorem. If I give you a sequence of moments that accumulates, then yes, it will uniquely determine. Now, normally in probability, you don't have a sequence of moments that accumulate. You have first moment, second moment, third moment, fourth moment. You need to look at things like the root-tooth moment. You have to look at a sequence of moments that accumulate. And then you can use this to get a proof of the central limit theorem. Okay, so this was a somewhat technical result. We'll see later in this course, I believe, other uses of accumulation points. So what I want to do is I want to do more contour integration. So there's a couple of skills you should be getting out of this class, as well as a couple of answers. One of the answers you want to get is to the question, do I want to continue in pure mathematics? Right? The purpose of this class is to give you a sense of what math grad school would be like. Do you want to do this to yourself? Okay? There's also a couple of skills I want you to have at the end of the semester. The most important is, can you actually do a contour integral? Okay? So that's why it's worth doing a bunch of them. So I asked you to consider the integral from minus infinity to infinity of sine of x over x to the m dx. M is in 1 term. And this is such a rich problem, we'll probably spend the rest of today just talking about these integrals. So I asked you to consider this. Does anybody have a thought of which m is easier?
1.
Okay. And anybody have any idea of a contour to choose?
Well, in the book, they just the indented semicircle,
Okay.
but that's only for 0 to infinity.
Mm-hmm.
But
But we can double things. Now, all right, so I have not looked at the book. I will show you a backdoor way to solve this problem. I got into trouble on my old exams to get my master's because of this problem. So let's study the integral from minus infinity to infinity of sine of x over x dx. What's the first thing you should ask yourself?
where does this thing go?
Okay, where does this blow up? And the answer? Does it blow up at 0? No, it's 1 at 0. The expansion of sine is x minus x cubed over 3 factorial. This is well defined at 0. Is this function integrable? depends on your definition. Okay? Doesn't happen often in mathematics, but it depends on your definition. If I put in absolute values, this function is not integrable. So the integral from minus infinity to infinity of the absolute value of sine of x over x dx is plus infinity. And the reason is the denominator is decaying like 1 over x. And I can find large blocks where the absolute value of sine is between 1/2 and 1. It is not integrable in the classic sense. But this is a very nice function that it's alternating between positive and negative. And so if you plot it, so at 0, okay, so it's going to look something like this. Something like that. And so you have positive region, negative region, positive region, negative region, positive region, negative region, and they're in decreasing magnitude. So you have an alternating series of contributions. And so the integral does make sense. And so if you consider the limit as a and b go to infinity of the integral from minus a to b of sine of x dx, sine of x over x dx, this does exist, no matter how you go to infinity. So the integral here does make sense. But it's very important that we have this alteration between positive and negative, that the nice blocks are the same width. Okay? So it's a little bit of work to prove that this makes sense, but it does. Okay. Any questions on whether or not we should be doing this problem? We've now hopefully motivated that this is a problem that can be done, the integral makes sense. Now the question is, how do we find its value? So I need to choose a function, and I need to choose a contour. Okay, so anybody have a thought for what function I should use? F of z is?
I think you want an e to the iv somewhere. So.
E to the iz over z. Now, I could have also done g of z is e to the iz minus e to the minus iz over z. I have two choices for functions. The advantage of this is when z equals x, g of x is just sine. Let's see. I know, and I was going to say now I need a 2i somewhere, so I think maybe times 2i.
Yeah.
Over here, f of x is going to be cosine x plus I sine x over x. So if you want to integrate sine of x over x, which would you rather do, f or g? Hint, both answers are right. Someone to give you a reason why g is better. Don't have a cosine term, right? You want to integrate sine of x over x. Here's sine of x over x. Give me a reason why g of x is worse. You have two exponentials and they go in opposite directions. So the real question is, what is the behavior of e to the iz? Iz and e to the minus iz. Let's let z equal x plus iy, y greater than 0. Then this becomes e to the ix, e to the minus y, and this one becomes e to the minus ix, e to the y. So this function is decaying rapidly as y gets large. And this function is blowing up rapidly as y gets large. If I were to use this function, I would have to basically modify my contour for each piece. And I'd have to do one piece in the upper half plane and one piece in the bottom half plane. Now, the flip side is, unfortunately, this gives me a cosine of x over x, which I don't really want. But what's the integral of cosine of x over x from minus infinity to infinity? 0. But because the integral of cosine of x over x is 0, we're okay. So again, Cosine is an odd function.
Even.
I'm sorry, cosine is an even function. Cosine of x over x is an odd function. But we've got to be a little bit careful. What do we have to be careful about?
X equals 0.
X equals 0. Now, unfortunately, when x equals 0, this blows up. So what we would have to do is, break this up into the integral from minus infinity to minus epsilon plus the integral from epsilon to infinity. And then take the limit as epsilon goes to 0. That would be okay. So these are all the technical details you have to do. And you have to decide, which would you rather do? Would you rather play these games with cosine? Or would you rather have two different pieces to integrate? Okay, so the goal is we want to use the residue theorem. Okay? And so now, how do we use the residue theorem? Alright, so we need to choose a contour. Right? So does anybody have a thought for the contour we should choose? Anybody have a thought for the contour?
Indented semicircle.
Indented semicircle. Okay. Which function are we integrating, f or g? F. Do you want the indent going up or the indent going down?
Up.
Up, okay. Really?
I think so.
Okay. You can do it either way. I'm sorry, what was that?
His choice is doomed us all.
Nope. I'm not saying his choice is to himself. It's like playing Mafia. I can't give anything away. Why do you want indented up and not indented down?
Because our integral is going from negative infinity to...
Good, so one thing is the integral is now oriented in the correct direction. That's one good plus. There's actually another good plus too. There's now no poles inside. So those are two good reasons.
But wouldn't there... But even if you did it the other direction...
Well, if I do it the other direction... well, I'm sorry. The other path we could do is we could do this.
Oh,
That's another one.
I thought you meant...
No, we're never going to the bottom half plane. No. Never. We could go like this. And now if we do this, the function e to the iz over z has a pole at z equals 0. Because the Taylor series of e to the iz starts off with 1. It looks like 1 over z. So if we do it like this, now we have a residue inside. By doing it this way, we don't have to worry about the residue. So I think this is a superior choice. And I was deliberately trying to, see if anybody would switch by resistance. This has two good things for it. It's oriented in the right way, and it doesn't have the pole inside. Okay. So now we have our contour. And so now we want to integrate the function from over a gamma of e to the iz over z dz. And so we're going to have a lot of pieces. So this is minus r, this is epsilon, we'll call this gamma epsilon, we'll call this r, and we'll call this big curve here gamma r. So first of all, what does this whole integral equal? 0, right? Integrating a holomorphic function in a region. I can put this region in an open set and still miss the pole. I get 0. Along the x-axis, I get the limit, well, I'm sorry, I don't have the limit. I have the integral from minus r to minus epsilon, plus the integral from epsilon to r of cosine x plus I sine x over x dx. Now I have plus the integral over gamma epsilon. And we have to remember gamma epsilon is going in the wrong direction. Of e to the iz over z dz. Right? And now we have plus the integral over gamma r of e to the iz over z dz. Alright. The first integral isn't that bad. The cosine drops off, and in the limit the sine is what we want. Is everybody comfortable with the first piece? Cosine x over x is odd, not a problem. Oh, this is technically right, but I really shouldn't write it like this. I dropped something. I dropped what? 1 over 2 pi I. Right? Because it equals 0, am I allowed to just drop it? Technically, I should put it in y. Why the hell do I want to multiply 0 by 2 pi I? It's for other problems when it's not 0. You want to just get in the habit of always writing 1 over 2 pi I. If you forget it, it's going to be bad for some other problems. For this problem, it won't make a difference at all. Alright, so we're okay on this integral. Cosine x over x is odd, no problem. Sine x over x, hey, that's what we want. That's good. Now we have to integrate e to the iz over z. That's not so bad. This is one of the standard integrals we've been doing. And so really, when we do the Taylor series expansion, all that matters here is the first term. So e to the iz over z is 1 over z. Then the next term is going to be plus I. The next term is going to be minus z over 2 factorial, yada, yada, yada. What can you tell me about the integral of all of these pieces when we're on the circle with radius epsilon? What's going to be the integral from, what's the contribution of this going to be?
0.
It's essentially going to be 0, right? It's a Taylor series, it converges. It's going to be at most basically some power of, some multiple of epsilon. The perimeter is going to be epsilon. So really, if z is sufficiently small, this is going to look essentially like absolute value 1. Because I has absolute value 1. For z very, very small, the rest doesn't really matter. So you can show that this is bounded by 2 if epsilon is small. So its integral is less than or equal to an absolute value 2, and then what's the perimeter of that circle, or that half circle? Pi epsilon, which tends to 0. So is everybody comfortable that this piece doesn't contribute in the limit? And the cosine piece goes to 0 in the limit. Oh, sorry.
Well, no,
Yes. I forgot. There's one other part of this term. There's the 1 over z. So we just have to integrate that. So we have to integrate 1 over z dz over gamma epsilon. All right, well, let's write z. Z is epsilon e to the I theta. dz is epsilon I e to the I theta d theta. And what does theta run from? Pi to 0. So this is equal to the integral from pi to 0 of 1 over z dz. Oh, well, look, z is epsilon e to the I theta. I divide by z, so I just get I d theta. That's not a hard integral to do, right? That's just going to be minus pi I. So this piece here, sorry, it doesn't go to 0. It goes to minus pi I. Yes?
Sorry, you lost me on that very last step. How you went from...
Well, dz is e to the epsilon I e to the I theta d theta. Z is epsilon e to the I theta.
Oh,
So when I look at dz over z, the epsilon e to the I thetas cancel. And I just get minus pi I. So the question is this looking reasonable? What do you expect this integral to be?
0.
0. And I have an imaginary number. I have I times sine of x over x minus something equals 0. So I'm getting the integral of sine of x over x is going to be pi. Do you believe that it can be pi? Why?
It's a trig function.
Trig function, right? Not surprised that pi shows up. Why else is this reasonable?
Positive?
Positive, right? If you think of the plot of sine of x over x, It starts off really high and positive, and now I have the oscillation. I expect a positive number. So again, these are great tests to do as you're doing the calculation. It's looking good. I'm getting a pi, and I'm getting a positive value for the integral of sine of x over x. All that's left to do is what? The last piece, which is trivially 0, and I leave it as the last piece is the difficult one. What would you love to do?
Make it go to 0 like that, and I go to infinity.
Okay. And so the numerator is bounded by 1, because I have e to the ix, e to the minus y. So the numerator is bounded by 1. What does the denominator look like? It looks like the absolute value of r. So this is bounded by 1 over r. What's the length of the upper circle? Ah, crap, right? It's not enough.
Why is it bounded by 1 over r?
Well, e to the iz is e to the ix, e to the minus y in the upper half plane. E to the ix is absolute value 1.
Right.
And e to the minus y is clearly going to be at most 1. So the numerator is at most 1. The denominator is of size r. So I can bound this trivially by 1 over r. Okay? I can bound it trivially by 1 over r. Are there any physicists in this part of the room who are also tired? We should make sure the M&Ms freely circulate. So just pass them around. Why is this not good enough? Well, the problem is this is decaying like 1 over r, but what's the length of the arc? Pi r. So their product is of size pi. That's not going to 0. We need additional decay. If I just crudely approximate the numerator by 1, this is not good enough. So other than giving up, what could we do?
Approximate better.
Approximate better, right? When in doubt, approximate better. Take more terms. Okay, so how could we take more terms? What could we do? Well, we could try to exploit the fact that we have e to the minus y. That has huge decay, right? So this is going to be a lot like one of our homework problems. So all that really matters now is this arc. And I have e to the ix, e to the minus y over r. And if I take the absolute value, so in fact the e to the ix doesn't even matter, so if I just look at the absolute value is e to the minus y divided by r. Where does this function have the most decay?
X equals 0.
X equals 0, right, when y equals r. So here, my decay is great. Where are the troublesome points? When I am at either plus r or minus r on the horizontal axis. So what I want to do is I want to make 2 cuts. And I want to split the arc into 3 pieces. So over into here, I'm going to have most of the length. Okay? And as long as I have most of the length here, if I have any amount of decay, sufficiently large, I will be in great shape. Then over here, I'll bound the function by 1, but I'll make those arcs really small. So how big could that arc be? It can't be larger than what? It can't be larger than 1 over r. Why can't it be larger than 1 over r? Because
then you have 1 over r squared decay with only 1 over r, or with r length.
look at our function is e to the minus y over r. I could have this almost as large as r and be okay. Right? In terms of the length. As long as I'm approximating e to the minus y by 1, could I have this length be square root of r? Yeah, because my function still has the decay from 1 over r. So I'm going to have some critical angle theta r. And I'm going to let theta r be r to the delta. Clearly I want delta to be less than 1. If delta is of size 1, then I have an arc of length r, it's too big. But if I take a smaller value of delta, I'm fine. The smaller value of delta I take, the smaller that is. Well, the smaller that is, the worse bound I have up over here. Because my bound from up over here is coming from this value here. And that gives me my little extra decay. So you can make these little white triangles and see if you've gone up height, if this angular measurement is, I'll be careful as to how I want to write this. If this length over here, I'm calling this length here r to the delta. The question then becomes, what's the value of theta? What's the value of this point? So I find it's very useful for problems like this to have a free parameter delta. I don't know ahead of time what I want delta to be. If you had to guess, what would you guess a good delta to be? You need to give me a delta less than 1. Half. Odds are if you just try delta equals a half, you should be okay. So one thing is you could draw the triangle. And so here's radius r, and then this length here is r to the delta. We need to figure out what is this value of y. Because on this big arc here, I can now replace e to the minus y with whatever that height is. Well, how do I get the angle? The whole angle is, the whole perimeter is 2 pi r. The length of this is r to the delta. So the angular measurement is going to be r to the delta over 2 pi r. This suggests maybe a slightly better choice. Instead of r to the delta, maybe I should take, for the length of this arc, maybe I don't want the length of the arc to be r to the delta. What could I do to make my algebra a little bit simpler?
Minus 1? R to the delta plus 1?
Nope. 2 pi. So that the 2 pi's would cancel.
Okay.
The whole circle has angular measurement 2 pi r. That's the perimeter. So maybe it would actually be better to take 2 pi over here. So for this length, maybe I should take it as 2 pi r to the delta. And now if I do that, this angle here is r to the delta over r. And now I can try to figure out what's this height going to be. Well, the height is going to be the sine of r to the delta minus 1.
Times r?
Times r, thank you. And so now if I expand this out, I get r times r to the delta minus 1 minus r to the delta minus 1 cubed over 3 factorial, etc., etc., etc. Delta is less than 1. This is a small number. Does everyone agree that it's essentially just given by the main term? That the other terms don't really matter? When r is enormous, r to the delta minus 1 is much, much larger than r to the delta minus 1 cubed. This is a number that's much less than 1, and I'm cubing it. So this is essentially r to the delta minus 1 times r. And so you can show that it's greater than or equal to 1/2 r to the delta. All of this stuff here can't do more than knock off, say, half of the big stuff. So again, you want to go through these arguments very carefully. I'm splitting it up. It turns out here this is very different than the homework problem. In the homework problem, we had a very small arc. Here I have a large arc. It's of length square root of r. It's of length r to the delta. But you have to remember, r to the delta is small relative to the whole arc of length r. Okay? If I put this on the web, I will try to replace the r's with the real letter. Okay? we have big arcs and small arcs. Here we have a big arc, but it's small relative to the parameters of interest. We still have an r in the denominator, so I can take it as large as r to the 1/2. I can even take it r to the 1 minus epsilon without any problem. The advantage now is the integral over here and here is negligible. Now the integral over the main part, I have an e to the minus y. The worst case for me is if I happen to be right here. Well, if I'm right here, I get 1/2 r to the delta. And so what I'm left with is, even in the worst case, I get e to the minus r to the delta over r. And what's the length of this whole segment? It's technically going to be pi r minus 2 times 2 pi r to the delta. But do I really care about that thing that I'm subtracting? No. So this is less than or equal to, the r's cancel, pi e to the minus r to the delta. And that goes to 0. And that finishes the problem, and that proves it. So again, the trick in this problem is splitting the contour. Why was this problem such a hell to do?
Because we had to deal with the...
We had to deal with that. So I was a smartass many times, and in taking my journal exam at Princeton on complex analysis, they asked me to do this integral. And I asked if we had to use complex analytic techniques or if we could do other things. There's a way to avoid a lot of this nightmare. So I'm going to just show you a quick calculation. So what's the other problem we haven't considered today?
Squared.
Let's let u be the sine of x squared. dv is 1 over x squared dx. du is 2 sine x cosine x dx, also known as the sine of 2x. v is negative 1 over x dx. Oh, so negative 1 over x. So this integral is uv at minus infinity infinity minus the integral of v du. Well, when I do uv at minus infinity, uv vanishes. Okay? Minus and a minus becomes a plus, and I get the integral from minus infinity to infinity of the sine of 2x over x dx. What can I multiply by? 1. And now change variables, and you get sine of x over x dx. The integrals are the same, but now my denominator up top will be a z squared. So play with that as another way to attack this problem. And you'll see how you can avoid the mess of that stuff there. The problem is you need the insight to actually go backwards. So what really happened was we were given sine squared x over x squared when I was an undergraduate in complex, and I noticed that by integrating by parts, I could reduce it to sine of x over x. You can actually go in either direction. And this is a really nice way to simplify things. Can I find a function that has the same behavior as what I want, but is a little bit more tractable? And this gets me an extra z in the denominator, and I don't have to deal with all those arcs. The problem becomes much easier. Yes?
Can you replace 2 with other things like 3 or 1.5?
For which?
For,
Oh, for here?
yes.
That's a good question, is to see if you kept integrating by parts, how many things you could do. So I'll make that extra credit. Can you make this problem work for anything else? Can you do sine of x to the 4th over x to the 4th? Or is this somehow really special about 2? Okay.